Hello students, in last class we have discussed about center tapped full wave rectifier. In this session we are going to analyze center tapped full wave rectifier. The first analysis parameter is DC output current. What do you mean by DC output current? It is the average value of current I indicated by IDC, which is given by 2Im divided by pi, where Im is the maximum value of current. Similarly, you can find out DC output voltage indicated by VDC. So VDC you can write it as the average value of DC output voltage. VDC is equal to 2Vm divided by pi, where Vm is the maximum value of output voltage. And the second parameter is RMS output current indicated by IRMS. It is the RMS value of output current and is given by Im divided by root 2. Similarly, you can find out RMS value of output voltage VRMS is given by Vm divided by root 2. And the third parameter is ripple factor indicated by R. All of you know what you mean by ripples. The unwanted AC component present in the output of rectifier is called ripples. The ripple factor is a measure of the amount of AC component and it is expressed in terms of ripple factor. As the AC component is undecided, the ripple factor should be smaller as possible and the ideal value of ripple factor is 0. For a center tapped full wave rectifier, the ripple factor R is equal to 0.483. Remember this value, R is equal to 0.483 for center tapped full wave rectifier. So as compared to half wave rectifier, for an half wave rectifier, the ripple factor is 1.21. So as compared to half wave rectifier, the ripple factor is very less. So we can say the output of full wave rectifier has very less AC component. And the next parameter is efficiency indicated by eta. It is the measure of ability of a rectifier to convert input power into DC power. So efficiency eta is equal to 81 into RL divided by RL plus RF, where RL is the load resistance and RF is the diode forward resistance. That means the resistance offered by the diode when it is in conduction, that is in forward bias mode. Diode forward resistance. So the maximum efficiency can be attained by using the ideal diodes. For an ideal diodes, the RF value, the diode forward resistance is 0. So you will get maximum efficiency as 81%. For an half wave rectifier, the maximum efficiency is 40.5%. For a center tapped full wave rectifier, the maximum efficiency is 81%. And the fifth parameter is peak inverse voltage. What do you mean by peak inverse voltage? It is the maximum voltage at which appears across the diode in the rectifier when the diode is not in conduction. That means diode is in reverse bias mode. So for a center tapped half wave rectifier, PIV is 2 times Vm. That means 2 times maximum value of output voltage. So as compared to half wave rectifier, this one is a very high value. For a half wave rectifier, peak inverse voltage is Vm. So the greater peak inverse voltage is a disadvantage because diode having the greater breakdown voltage are costlier. For a safer operation, the PIV should be less than breakdown voltage. So the diode we have to use a diode which should have a greater breakdown voltage. So these type of diodes are costlier. And the next parameter is form factor, which is the ratio of RMS value to the average value. And for a center tapped rectifier, it is 1.11. For a half wave rectifier, remember what is the value of form factor? 1.57. But for a center tapped rectifier, form factor is 1.11. And the next parameter is peak factor, which is the ratio of maximum value to the RMS value and is given by root 2. And the next is frequency of output. So before explaining the frequency, what is the value of frequency of the output waveform, look onto this diagram. The first waveform is the voltage at the secondary. Recollect the working of center tapped full wave rectifier. At the secondary side, we have two winding, and the voltage across each winding is indicated by VA or VB. So let this one is the voltage at the primary winding, that is VA. For a secondary winding, that means the other winding, what is the voltage? The magnitude is same, but the polarity is reversed, opposite. So here I am showing the output voltage across the first winding in the secondary. So that is VA. So this one is pi, and this is 2 pi. And the output voltage, the next waveform is output voltage indicated by V naught. So for a period, for the consider the waveform VA, the period of the waveform VA is T. So here I am indicating the time period. And this is the fundamental time period T. It is the time interval at which the signal repeating itself. So this is the fundamental time period indicated by T. So for this waveform, the fundamental time period is 2 pi. This is 2 pi. Axis is omega t. Okay. Then look on to the output waveform V naught. So what is the time period, the fundamental time period of the output waveform? So first I will mark the output waveform, time period of the output waveform. So this one is the time period of the output waveform as compared to the output voltage of VA. I can say this time period is T by 2. This time period is T by 2. So the time period of the output waveform is half of the time period of input waveform. So I can say the frequency of the output waveform is 2 times the frequency of supply. That because the time period of the output waveform is T by 2, where T is the time period of input waveform. So the frequency of the output. So the frequency of the output the output can be voltage or current. The frequency of the output is 2 times frequency of input voltage or current. Okay, so the frequency of the output is 2 times frequency of supply. Okay. So since the time period of output waveform is T by 2, the frequency of the output will be 2 times frequency of supply. And the next parameter is transformer utilization factor. The full wave rectifier, the center tapped full wave rectifier is a combination of two half wave rectifiers, as we have seen the working while I am explaining the center tapped full wave rectifier. you recollect that one, you know that the full wave rectifier is a combination of two half wave rectifiers. So therefore, the transformer utilization factor with respect to the secondary winding is 2 times transformer utilization factor of half wave rectifier. So in this case, the transformer utilization factor of a center tapped full wave rectifier, we have to find out transformer utilization factor at the secondary winding as well as primary winding. Finally, we have to average these values. So the transformer utilization factor at the secondary winding of a center tapped rectifier is 2 times transformer utilization factor of half wave rectifier. So this is 2 into 0.286 into RL divided by RF plus RL, which is equal to 0.57 into RL divided by RF plus RL. Then we have to find out transformer utilization factor of primary winding, which is equal to 0.81 into RL divided by RF plus RL. So finally we have to average these two values, TUF at the secondary winding and TUF at the primary winding, which is equal to 0.57 plus 0.81 divided by 2, which is equal to 0.69. This is the maximum average value. This is the maximum average value of transformer utilization factor. How to get the maximum transformer utilization factor? By putting RF equal to 0. When the diodes are ideal, we can put RF equal to 0 so that we will get maximum transformer utilization factor. So for a center tapped full wave rectifier, the maximum transformer utilization factor is equal to 0.69, whereas in a half wave rectifier, the maximum transformer utilization factor is 0.286. For a center tapped half wave rectifier, it is 0.69. Next, we are going to see what are the advantages of center tapped full wave rectifier. So the center tapped full wave rectifier have smaller ripple factor, a ripple factor of 0.483 as compared to half wave rectifier. For a half wave rectifier, it is 1.21. So compared to half wave rectifier, this one is a very smaller value. And the next one is greater efficiency. Center tapped full wave rectifier has maximum efficiency of 81%, whereas half wave rectifier it is 40.5. And the next is greater transformer utilization factor. For a center tapped half wave rectifier, the maximum transformer utilization factor is 0.69. In half wave rectifier, it is 0.286. And the next advantage is greater DC current and DC voltage. For a center tapped half wave rectifier, the DC output current is 2 Im divided by pi, whereas in a half wave rectifier, the DC output current is Im by pi, exactly double. For a full wave rectifier, the DC output current is double that of half wave rectifier. And the last one is filtering of AC component is easier because it has smaller ripple factor, so the filtering of AC component is easier. The filtering can be achieved by using capacitor filter or induction filter, so on. Here the filtering is easy. And the disadvantage of center tapped full wave rectifier is it has higher peak inverse voltage of 2 Vm, whereas in half wave rectifier the peak inverse voltage is Vm, but here it is 2 Vm. So we have to use a diode with a greater breakdown voltages. Such type of diodes are costlier. So this is the first disadvantage. And the second one is it is necessary to use center tapped transformer which is bigger in size and costlier. The main hardware component of the center tapped full wave rectifier is the center tapped transformer. Then what do you mean by the center tapped transformer, or what is the difference of center tapped rectifier as compared to the normal transformer? For a center tapped transformer at the secondary winding, it has again the secondary winding is split into two halves. Okay, remember or recollecting the working of center tapped full wave rectifier. The secondary winding is split into two halves. and these two halves have equal winding, but the voltage developed across these two windings have equal in magnitude but in opposite polarity. This makes diodes, each diodes conduct at a different interval of time. Okay, so the center tapped transformer are bigger in size and costlier. Next we are going to see the second type of full wave rectifier, and it is bridge rectifier. So the diagram shown in this PPT is the circuit diagram of bridge rectifier. It uses a normal step down transformer. So in center tapped full wave rectifier we are using center tapped transformer, but in the case of bridge rectifier we are using a normal step down transformer and a bridge network of 4 diodes. So here diodes are arranged in a bridge structure, that is why it is known as a bridge rectifier. So here we are using 4 diodes which are connected in a bridge network manner, and we are using a normal step down transformer. Okay, then the RL is the load resistance. So the concept, so the look on to the primary winding of the step down transformer. The input to the supply voltage applied to the primary winding is a pure AC. So in India we can say this one is a 220 volt, 220 to 240 VRMS value. This is VRMS value and it is 50 hertz, 50 to 60 hertz. It is a 50 hertz signal. Okay. So here we are using step down transformer because I have already stated that all the electronic components are working in the range or 5 to 10 volt or 5 to 20 volt. So the voltage from the line, electric lines is 220 volt RMS value. So we have to step down to operate all these diodes. All the electronic components need a lesser voltage in the range of in the tens of volts. Okay, so we have to step down the value. So we can use a step down transformer. So here I am indicated by the winding at the primary is indicated by N1 and the number of winding at the secondary is indicated by N2. So here N1 is greater than N2. Okay, for a step down transformer the number of windings at the primary is greater than that of secondary. For a step up transformer this will become reverse, N2 is greater than N1, but here we are using step down transformer. So the voltage developed at the secondary winding is indicated by Vi, and this one is applied to each of these diodes D1, D2, D3 and D4, and across the bridge network I am connected a load resistor indicated by RL, and the voltage across the load resistor is indicated by V0, which is the output voltage. So V0 is the output voltage. So I can say the voltage at the secondary is indicated by Vi, and Vi also a pure AC signal. Okay, because we are at the primary we are applying a pure AC signal, at the secondary also at the voltage developed at the secondary winding is also a pure AC, but smaller RMS value, a pure AC voltage, but this voltage developed at the secondary winding has a lesser RMS value. So the pure AC voltage having smaller RMS value. RMS means root mean square value. For an AC, the one of the property or characteristics of AC signal is we are expressing the AC signal in terms of its RMS value. Root means square value. For a DC quantities, it is not a problem. The RMS value and average values are same. But for an AC quantity, that means whether it is AC voltage or AC current, we are expressing in terms of RMS value. So Vi is a pure AC voltage having smaller RMS value. So and this voltage is applied to diode. So now we are going to see the working of bridge full wave rectifier. So here I am showing the output waveform. I will explain that, don't worry. First look on to this output or input voltage VI, the voltage developed at the secondary winding indicated by VI. This is also a sinusoidal signal, pure AC voltage, and the axis is x-axis is omega t and the y-axis is voltage, and the maximum input voltage is indicated by Vm. The output graph of output V naught is, I will explain just a second. First I will explain the operation. After that I will return to the output waveform. Okay, so already I told that the input voltage or the voltage developed at the secondary winding is a pure AC voltage having smaller RMS value, and mathematically I can I can express the voltage developed at the secondary winding is VI is equal to Vm sine omega t. Okay, so consider the first half cycle and the omega t from 0 to pi. So look onto this, the previous waveform VI. Look onto the waveform of VI when omega is from 0 to pi. When the omega is from 0 to pi, the input voltage or the voltage developed at the secondary winding Vi is a positive value in the positive value. That means first we are considering the positive half cycle. So when omega t from 0 to pi, Vi is a positive value. That means we are considering the positive half cycle. So in the positive half cycle, I can write Vi is in this range. When the omega t from 0 to pi, Vi is positive value. That means we are considering the positive half cycle, positive value. So I can next step is when the Vi is positive, which diodes are going to conduct. Again I am going back to the circuit and look on to this diagram or the circuit diagram. When the Vi is positive, which diodes are in forward bias? So what is the condition to which diode is conducting? What is the condition at which diode is conducting? When we are applying a higher voltage at the P side as compared to N side, so that the diode becomes forward bias. That means, so this is P side and this is N side. When we are applying a higher voltage, for example 5 volt, and we are applying the voltage at the N side is 4 volt. So here the voltage at the P side is greater than that of N side. So I can say this diode starts conducting, or the diode is in forward bias mode. So again look onto this diagram. The Vi is a positive value. So Vi is a positive value. So that means here like that. Here I am. Vi is a positive value. Okay. So Vi is a positive value. So this positive comes here also. Here positive, and this is negative, and here comes the negative. Okay. So and here also positive. So then look on to the D1. Here D1, the positive voltage is applied to P side of diode D1. P side of diode D1. So D1 is in forward bias mode. So then consider D4. D4, the positive voltage is applied at N side of D4. So the D4 is reverse bias. Then consider D3. In D3, the negative voltage is applied to N side of D3. So D3 is in forward bias, because here I am applying a negative voltage to the N side as compared to P side. So D3 is in forward bias. Then D2. In D2 also I am applying negative voltage at the P side. So D2 is in reverse bias mode. So when Vi is in positive half cycle, or Va is in positive value, the D1 and D3 are forward bias. That means they are starts conducting, and D2 and D4 are in reverse bias. So I can say Va is positive D1 and D3 are in forward bias mode. In short, I am writing say FB. FB means forward bias mode. And D2 and D4 are reverse bias mode. Here I am written RB. RB means reverse bias mode. So to analyze the circuit, the reverse bias, when the diode is in reverse bias mode, I am replacing the reverse biased mode in a short circuit manner. That means a wire. Short circuit means connected with a simple wire. That means short circuit means they are not offering any resistance. So in forward bias mode, they are starts conducting. That means current starts flowing through that diode. So to analyze the circuit, the diode is replaced by short circuit when it is in forward bias. Then D2 and D4 are in reverse bias. The reverse biased diodes are replaced as open circuit. That means in reverse bias, these the diodes are not conducting. That means there is no current is flowing through that diode when it is in reverse bias. So to analyze the circuit, I am replacing reverse bias diode as an open circuit. Open circuit means there is no connection in between the two wires, like that. This is open circuit. And the short circuit means I am replacing diode as a symbol, like a simple wire. This is short circuit. So the position of D1 is this one, and the position of D3 is this one, and the D4 is in this position, and the D2 is in this position. Okay, so D1 is short circuit. Actually, here I am assuming the diodes, all the diodes are ideal. For an ideal diodes, it is replaced by short circuit when it is in forward bias, and it is replaced by open circuit when it is in reverse bias. And this is D3. This is also short circuit. And D4 and D2 are open circuit. Okay, here I am drawing only the secondary section only. Okay, the secondary side only. So, and this one is the voltage at the primary winding indicated by VI. And this one is the load resistor, and the voltage across the load resistor is output voltage indicated by V0. And then observe the diagram. What is the direction of current flow? Remember that current is always choose a low resistance path, and the current is always flows through a closed circuit path. The circuit should be closed one, then only current can flow. So in this diagram, the current is starting from this like that, then current is flowing flowing through this D1. It never goes to the D4 because the D4 is open circuited. So the current can't flow through the D4. The current chooses the D1 path. So D1, then RL, then like that, then this path. This jumper, here I am drawing one jumper. That means there is no connection in between these two wires. That's why here I am showing a jumper. Then current is flow this one, then through D3 and like that, and the secondary winding. Look onto this diagram. Now the circuit, the path is a closed one. So that current is flowing through D1, first D1, then the load resistor RL. I'm showing the D1, then the load resistor RL, then D3, then winding. Here I am also writing the winding. That means the secondary winding, then D3, then secondary, then also winding. So the path is a closed one, and the current is flowing. Okay, so here D1 and D3 are in forward bias mode, and D2 and D4 are in reverse bias mode, and the current starts or flowing like that winding D1, RL, D3 and winding. Okay, and next we are going to see the second half cycle. Okay, before going to the second half cycle, that means pi to 2 pi, look onto this output waveform. So when omega t from 0 to pi, the output voltage Vi is a positive half cycle, and the same waveform, the same shape, a positive half cycle voltage is developed across the load resistor also. So the both the at the shape of the input waveform and output waveform is same, a positive half cycle like that. This one, a positive half cycle. This is 0 to pi. Okay. Next we are going to see what happened when omega t from pi to 2 pi. So again I am going to our circuit diagram. Okay, when omega t from pi to 2 pi, look on to this waveform of Vi, input voltage. When omega t from pi to 2 pi, the Vi becomes negative. Vi is a negative value, negative half cycle. So Vi is a negative value, so I am writing this one is a negative with respect to the other term, minus plus. So the p side of D1 is a negative, n side of D4 is negative, n side of D3 is positive, p side of D2 is also positive. So look on to this diagram, I can say D1 and D3 are reverse bias, because for a D1 we are applying a negative voltage at the p side, and in the case of a D3 we are applying a positive voltage at the n side. So D1 and D3 are reverse bias mode, and the D2 and D4 are in forward bias, because for in the case of a D4 we are applying negative voltage at the n side, and in the case of a D2 we are applying positive voltage at the p side. Okay, so the D4 and D2 are in forward bias mode. So here I am writing that Vi, when omega t from pi to 2 pi, Vi is a negative value. And D1 and D3 are in reverse bias mode. That means they are not conducting. And the D2 and D4 are in forward bias. That means they are starts conducting. Okay, so the forward bias diodes can be replaced as a short circuit, and the reverse bias mode can be replaced as open circuit. Okay, so this is the place of D1 and this is the position of D4, and that this is D3 and this is D2, and this one is the load resistor and this one is the output voltage. Okay, so and this one is VI, the voltage at the secondary winding is VI, and the D1 and D3 are in reverse bias, so this one is open circuit. And D2 and D4 are forward bias, so these two are short circuit. Okay, then next is what is the current flow direction. So look onto this diagram. the current starts flowing the first from the D2 like that, the D2, then the load resistor RL, this is load resistor RL, then goes to D4 and again comes to the winding. So I am writing current flows through winding, secondary winding, then D2, then the load resistor RL, then D4 and again secondary winding. Here also secondary winding. Okay. So the current flows through D2 secondary winding, D2 RL, D4 secondary winding, and the cycle is repeating. So the current flows through a loop consists of D2, RL, D4 and the secondary winding. So consider the output waveform. The output waveform has also the same size as that of input voltage Vi. And look onto this diagram. Here, when the omega t from pi to 2 pi, the shape of the output waveform is like a sinusoidal, not sinusoidal. It is in a half cycle waveform, but it is in positive polarity. Okay, look onto the Vi input voltage Vi. When omega t from pi to 2 pi, the input voltage is also a half cycle. Yeah, the input cycle is also a half cycle, but it is a negative polarity. But this is a negative. But at the same time, the output voltage is also a negative half cycle, but it is in a positive polarity. So why the output voltage when the omega t from pi to 2 pi? In that time, how the output voltage becomes positive value. The reason for this that the current through secondary winding is the bidirectional or AC because the current flows in both in upward and the downward direction. But the current through the load resistor RL is unidirectional or the pulsating DC because remember listen, because it flows always in the downward direction or in one direction. That means consider when omega t from 0 to pi, what is the direction of current flow when it is flowing through the load resistor RL? D1, first current is starting from winding, D1 RL, so like that in downward direction, then D3 and winding. When omega t from pi to 2 pi, what is the direction of current flow when it is flowing through RL? Secondary winding, D2 RL. In this case also it is in downward direction. That is why I have stated that in both cases, that means in when omega t from 0 to pi and the pi to 2 pi, the current flows always in downward direction through RL. The current always flows in downward direction or in the same direction through the load resistor RL. That is why the output waveform when omega t from pi to 2 pi is a positive value. Okay, hope that you got the concept. In both cases, when omega t from pi to 2 pi and when omega t from 0 to pi and pi to 2 pi, the current flowing through the load resistor RL in downward direction or in one direction. So when omega t from pi to 2 pi, the output voltage also in the positive magnitude. So this is the working of bridge full wave rectifier. So again I will summarize the working of bridge full wave rectifier. It uses normal step down transformer and contains 4 diodes. They are arranged in a bridge manner, and when omega t from pi to 2 pi, that means second half cycle, pi to 2 pi, there are two diodes are conducting. That means D2 and D4. D2 and D4 are conducting when omega t from pi to 2 pi, and when omega t from 0 to pi, D1 and D3 are conducting. Okay, then in both cases the current flowing through the load resistor is in the same direction. So the output waveform is in a unidirectional form or in a pulsating DC form.